Hello and welcome back everybody to geometry. Today we are looking at the last set of the identities, or at least, for the time being until you get back into pre-calculus for Moise in this case. So all the identities that we've learned so far are listed underneath. You can see there are quite a few of them. So there are, looks like it's going to be 7 in this case. And I kind of I guess organize them in a way that it's a little bit easier to memorize. So the first one is the big one anyways. It's going to be sine squared plus cosine squared of the same angle is always equal to 1. Then there is the tangent of theta, which is the same thing as sine divided by cosine of theta. Okay, so those two are pretty essential. The ones underneath over here, these are the ones that we derived in the last section. Cosine of negative theta is equal to cosine of theta. And then we have sine of negative theta is equal to negative sine of theta. And finally, for the ones underneath that one, is tangent of negative theta is equal to the negative tangent of theta. Those we derive by looking at the unit circle and looking at it geometrically as to the location of where theta and negative theta is going to be. As for the last two over here, these are going to be a little bit different. We actually derive geometrically as well. Cosine of pi over 2 minus theta is equal to sine of theta, and also sine of pi over 2 minus theta is equal to cosine of theta. So those, I think we kind of derive from just using a right triangle to see how they actually works out. So the ones on the right where you have the blue dots, those are not really essential for the most part. The ones that are essential are the ones actually on the right, because they can be used to derive like stronger ones, other ones. Now, there are some that are not in the book, so I'm going to go ahead and write these down because eventually they are going to come in handy, but for the time being, it's just good to kind of mention them just in case. If you take our identity over here, the sine squared plus cosine squared, and by the way, that's what they call the Pythagorean identity because it's derived from using the Pythagorean theorem. What I can do is I can take my equation right here. Let me just kind of write it over here first, just rewriting it. So sine squared theta plus cosine squared of theta is equal to 1. Now, for this equation, if I take everything and divide by, let's say, sine squared of theta, then we're going to get the following. So I have 1 plus, let's see, and I'm going to kind of write that out on the side. I'm going to divide by sine squared of theta to everything. So 1 plus cosine squared divided by sine squared, that is the same thing as cotangent squared. So that I can replace over there. And then is equal to 1 divided by sine squared. That is the same thing as, let's see, that is going to be cosecant squared then. Okay, so that is going to be another identity. Now, also, I can take that and say, hey, let's not divide by sine squared. Maybe I can divide by cosine squared. And if I do so, then my identity now becomes sine squared divided by cosine squared, which is the same thing as tangent squared. And then plus cosine squared divided by cosine squared, that's going to be 1. And all of that is equal to 1 divided by cosine squared. That is going to be equal to secant squared of theta. So these three right there, those are all the three that are under the category of Pythagorean identities. Do you need to know them for the time being? The answer is going to be no. But again, in pre-calc, they will actually become more relevant and more useful then. Okay, so for today, what I want to do is I want to talk about something called the composite identity. So meaning I want to know what is maybe like, say, the cosine of a plus b equal to. Okay, I want to know what is the cosine of a plus b. My pen looks like it's going to be slowed down right now, so hopefully you can bear with me for this one. And if you're wondering to yourself, okay, cosine of a plus b, well, according to algebra, maybe that's the cosine of a plus cosine of b. So maybe this is equal to cosine of a and then plus the cosine of b then, okay? Because, maybe we could do the distributive property. But it turns out that that's actually not the case. And we can do this by showing a counterexample. Let's say that we want to solve for the cosine of 135 degrees, right? Now, if I take that 135 degrees, I can go ahead and break it up to the following. That's going to be equal to cosine of maybe like say 90 and then plus cosine of 45 degrees. because according to, oh, actually, hold on. Let me kind of rewrite this part over here. I can look at this as cosine of 90 plus 45 degrees, okay? So changing that 135 to 90 plus 45, that we can definitely do. Now here, if we were to say, okay, this is going to be equal to cosine of 90 plus cosine of 45, because hey, maybe it's a distributive property in this case, you can see where that actually is going to fall apart, because this part over here, cosine of 90, that is equal to 0. And then cosine of 45, that is equal to root 2 over 2. But if you remember, on the unit circle, cosine of 135, that's in quadrant 2. And that's actually equal to negative root 2 over 2. So you can see the answer is not going to be the same thing. So it's not as simple as just kind of distributing the cosine of it. So what I want to do is I want to actually derive a formula for cosine of a plus b. Also, maybe cosine of a minus b. And then sine of a plus b, sine of a minus b. So those are the composite functions that I'm talking about. So here, if you can kind of like take a look at it, as I said, the question right here. What are cosine of a plus b, cosine of a minus b, sine of a plus or minus b, and then even go further as saying what is a tangent of a plus or minus b. Well, let's go ahead and derive one of them, and then the other ones, I'm going to go ahead and put them up, and you can go ahead and, pause the video if you want to take a look at it later on, but we're just going to go ahead and derive one just to give you an idea, okay? So here, I'm going to go ahead and focus on the right-hand side. You'll notice that I have created quadrant 1 of the unit circle, and what I'm going to do is I'm going to look at two positions on the unit circle. I'm going to look at some point P right here, and I'm going to look at some point Q over here. For my point P, I'm referencing the angle, the central angle, as angle B. Okay, so you can see that underneath. So as a result, then that's where I'm getting the cosine of B and also the sine of B from, because again, the central angle is going to be B. At point Q, I'm going to do the same thing, but referencing to a different central angle we'll go ahead and call A, which where A is going to be smaller than B in this case. So that means the x-coordinate is going to be cosine of A, and then that y-coordinate is going to be sine of A. Okay, so we have those 2 points, P and Q, on a unit circle. And needless to say, over here, O is going to be my origin, which is going to be 0, 0. Okay, now as a result, I have created a wedge of the circle. OPQ, that's a wedge of the circle, like a piece of the circle. What I'm going to do is I'm going to go ahead and look at the angle in between the two. Since the larger angle is B and the smaller angle is A, then that means that this angle in between them should be, according to my picture, B minus A then. Okay, so that's the first setup then. Now, here's the part that gets a little tricky. I'm going to take this wedge that I have created and I'm going to rotate it downward, so then that way we're on the 3 o'clock position. So that's to say point Q is going to be rotated down to the x-axis. Point P is going to be rotated down to some place over here. And then as a result, we're going to have that same wedge, but this angle is going to be B minus A as the central angle. And that's where this picture on the left is going to be. Okay, so that picture on the left is basically the same congruent wedge that we have on the right, except we're going to rotate it downward so that the central angle is going to be B minus A in that picture then. So Q translate into the point 1, 0. And then point P is going to translate to a new position where the angle, remember, the central angle is supposed to be B minus A. So that means that this will say cosine of B minus A and sine of B minus A. Okay, so that's where those two pictures are coming from. All right, now here's the next part. Next, what I want to do is I want to take a look at PQ, the chord. Okay, I want to take a look at PQ, the chord. So if I can, I'm going to go ahead and draw it over here. PQ, not the arc, but rather PQ, the chord. I can solve for the length of PQ, the chord, using the Pythagorean theorem, and that right there is underneath over here. So you can see the change in x squared, which is cosine of B minus cosine of A quantity squared, plus the change of y squared, which will be sine of B minus sine of A quantity squared, all inside the square root. So that's going to be PQ right there, the chord. On the left-hand side, if you remember, we said that this arc is going to be, or this wedge is actually going to be congruent to the one that's over here on the right, PQ. Over here, similarly, I'm going to solve for the length of this chord over here. which is supposed to be congruent to the chord that I just created. Now, according to distance formula on the left-hand side, then we can set up the following then. We can say cosine of b minus a minus 1 squared, the change in x squared, and then plus the change of y squared. So that's going to be sine squared of b minus a minus 0 squared. And then if I take the square root of that, that is going to be the length of that chord. And these two, I can set them equal to each other because, once again, those two chords are congruent to each other. Now it's just a matter of algebraing all of this, so then that way you can see where we can get all of this then, okay? So the first part, I kind of like multiplied it out using FOIL. And then on the left-hand side, I'm using FOIL to multiply everything out. On the right-hand side, I'm also using FOIL to multiply everything out. And you can see that there are actually some terms that are going to cancel each other out. Note that this guy right here, cosine squared plus sine squared of the same angle, that is supposed to be equal to 1. And so 1 plus 1, that's going to be equal to 2. So 2 minus 2 cosine b minus a, so that's the left-hand side. On the right-hand side, I have a similar argument. Note that I have cosine squared of b plus sine squared of b, so that's equal to 1 according to my Pythagorean identity. Then we have cosine squared plus sine squared of a, and that's also equal to 1. So again, 1 plus 1 is equal to 2. So 2 minus, and these are just all the residual stuff that's in the middle. So on the left, on the right, you have a 2 that you can actually just go ahead and cancel out. So that 2 that I created on the left is gone. That 2 on the right that I've created is gone because of subtraction. And with what I have left right here, negative 2 cosine of b minus a is equal to this whole thing that's on the right-hand side. Now remember, focus is I want to solve for what is cosine of b minus a, right? Because I want a composite identity. So the last thing we're going to go ahead and do is divide everything by negative 2. And lo and behold, there we go. That's going to be our equation for the composite for cosine then. Okay, so cosine of b minus a is equal to cosine of a times the cosine of b plus the sine of a plus the sine of b then. Okay. All right, so now I want to know, okay, well, how do you actually use this then? Or what is this actually for? Well, then now what that means is we can actually solve for those angles that are not on the unit circle. So for example, what is the cosine of 15 degrees? Because if you think about like how do you get 15 degrees, that's the same thing as cosine of 45 minus 30 degrees. And 45 and 30, those are values on a unit circle that we do know. So we'll show that in just a little bit then. Okay. So then there are also the other composite angles, which, as I said, there are other composite identities, which I said, but for now, I'm just going to go ahead and show you, and you can pause the videos if you want to look at the derivation, but I'm not going to go over it because it's going to take a very, very long time if I actually kind of run over each one. So here's the one right here for deriving cosine of a plus b, or x plus y in this case, okay? But here, more importantly, I want to know how to actually utilize these composite angles. So here, let's go ahead and show the example then. I want to solve for what is the cosine of 11 pi over 12. Okay, 11 pi over 12. Now, for those of you guys that are still kind of like, juggling between the degree and also radian form, let me go ahead and write this over here in degree form. That is going to be 11 pi over 12, which is the same thing as 11 divided by 12 multiplied by 180 degrees. And if we clean that up a little bit, let's see, 11 multiplied by 18 divided by 12. We're going to go ahead and divide everything by 6. So that's a 3 on top, 2 on the bottom. So that is equal to, let's see, did I do it correctly? Yeah, so it looks like it's going to be equal to 33 over 2. Wait, that sounds kind of strange here. Let me see if I can get this right. 11, let's see, 12. And, oh, actually, I'm sorry. I did a little bit of wrong math over here. That's my fault. Okay, back up over here a little bit. Okay, so that's going to be 180 and then divided by 12. Divide everything by 6. So that is going to give me a 2 on the bottom and then a 30 on the top. And it looks like we can divide a little bit further. So that is going to be 11 times 15. So that is equal to the equivalent of 165 degrees. Okay, so that's the same, that's what it's equal to. So I'm asking for what is the cosine of 165 degrees, or if you want, you can write it as 11 pi over 12. Now, if it's a little bit easier for you to swallow the 165 pill, I'm going to go ahead and write that out as is right there. Note, 165 is not a value that's on the unit circle because remember, unit circle, they only have values that are multiples of 45s and also multiples of 30, right? 165 does not fall into any of those categories. But 165 is a combination of two numbers. When I add them, will give me 165. And those two numbers are some things that are on the unit circle. Okay, so here, let me just see if I can find two good combinations in this case. So 165, let's see, how about 135 degrees, right? That's one thing that we know on the unit circle. And then another one that I know on the unit circle is 30 degrees. So there we go. Okay, so that's going to be my composite setup in this case. Now, using the composite for cosine above, we're going to go ahead and solve for this now. So cosine of x plus y, that is supposed to be equal to cosine of x times cosine of y minus sine of x times sine of y. So x in this case is going to be equal to 135. Y in this case is going to be equal to 30. So according to my composite equation, that's going to be the cosine of 135 times the cosine of 30 degrees, and then minus the sine of 135 degrees multiplied by the sine of 30 degrees. Okay, so we keep cleaning it up now. These are all values, as again, we know on the unit circles because those are supposed to be memorized. The first one is supposed to be negative root 2 over 2 multiplied by the second one, cosine of 30 degrees, that is supposed to be equal to root 3 over 2. Then after that, we have minus sine of 135. That is the same thing as root 2 over 2. And then multiply by sine of 30, which is the same thing as 1 over 2. So finally, clean up my math a little bit. Looks like the top, there's going to be a negative root 6. And then we have a minus root 2. And all divided by 2 times 2, which is equal to 4. And be very careful, the top right there, you can't combine those two together because they you can't subtract when you have the root underneath above both of those. So this right here, that's going to be my final answer for the cosine of 165 degrees. So that's how you're supposed to use a composite function then. Okay. Here on the right hand side, just to give you a different variation, let's say I want to solve for what is the cosine of pi over 12. Again, think about values that are on the unit circles that will get you that pi over 12. If it's easier for you to see it in degree form, that's totally fine. If I do all the math right here, I'm pretty sure that's going to come out to be saying, what is the cosine of 15 degrees? Well, find a combination of two numbers where when you add or subtract them gives you 15 degrees. So here, let's go ahead and say cosine of, let's see, maybe I'll go ahead and change it up and do 60 degrees and then minus 45 degrees. Okay. So if I do so, then according to my trig identity, the one that I derived earlier, and let me go ahead and highlight it just to make things a little bit easier for you. So this is what it's supposed to be look like. The right hand side, it says supposed to be the cosine of A times the cosine of, sorry, I think I wrote it down wrong over here. Let me go ahead and erase it. Cosine of A times the cosine of B in this case, okay? And then plus the sine of A and then multiply by the sine of B in this case, okay? So if I go back over here, then this is supposed to be equal to cosine of 60 multiplied by the cosine of 45 because A is supposed to be equal to 60 and B is equal to 45 according to my, I guess, plugin in this case. And then we have plus sine of 60 degrees multiplied by the sine of 45 degrees. Okay, so that now gives you all these values that you know on the unit circle. Cosine of 60, that is going to be root 3 over, cosine of 60 is equal to 1/2 in this case. Okay, cosine of 60 is equal to 1/2 times cosine of 45 degrees, that is root 2 over 2. and then plus sine of 60 degrees, that is going to be root 3 over 2. And then multiply by sine of 45, that is going to be root 2 over 2. So cleaning everything up, I have a root 2 on top, I have a root 6 on the top, and then divided by the bottom, which is going to be 4. So that is going to be my cosine of 15 degrees then. Okay, and as you can see, it's just the negative of the other answer that I have on the left, because if you think about the geometry part of it, okay, on the unit circle, if I draw 15 degree over here, whatever the x value is over here, that is supposed to be, well, congruent all the way on the opposite side if I were to draw these two triangles. The x value over here is just going to be the negative of the one that's on the left because of congruency then. Okay, so it only makes sense that they are the negative of each other. All right, so as I said, for the other equations for composite for sine and also tangent, I'm just going to go ahead and leave it right here. So here's the derivation of it. And then also for tangent, here's the derivation of that also as well. And I'm going to go ahead and let you kind of like, let it sink in and pause the video if you need to watch it. And that's totally fine then. Okay. But again, deriving it and talking about it the entire time, that'll probably add on another 20-30 minutes into this video. Okay. So here they are. In conclusion, all the composite identities for sine, cosine, and tangent are these three over here. Okay. So cosine of a plus or minus b is equal to the cosine of a times the cosine of b minus plus, meaning that we switch the sign. If we use a plus, we use a minus. If you use a minus, use a plus. Okay. And then times the sine of a times the sine of b. Whereas for the sine of a plus b, that is going to be equal to sine of a times the cosine of b. And then plus minus, meaning that's the same sign that you use over here, cosine of a times the sine of b. Okay, so sine, cosine, cosine, sine, whereas for cosine is cosine, cosine, sine, sine. And finally for tangent, that is going to be a little bit more difficult to memorize, but it's still doable. Tangent of a plus b or minus b is going to be equal to tangent of a plus or minus the tangent of b in this case, and I wrote it wrong, so let me go ahead and make that small little change right here. Okay, so this guy is supposed to be a b, so I apologize for that one. And then all divided by 1, and then plus or minus the tangent of a times the tangent of b. Okay, so once again, what I'll do is I'm going to go ahead and show you how to use these composites, so then that way you can kind of try them out yourself. So let's say in our example in this case, okay, what I'm going to do is I'm going to say, let the sine of an angle be equal to 24 over 25 as a ratio, where the angle is supposed to be somewhere located in quadrant 2. Okay. Then in addition to that, what we're going to do is we're going to have another angle. We'll go ahead and say B, and the tangent of that angle B is going to be equal to negative 3/4, where B is going to be located in quadrant 4. What I'd like to do is evaluate what is the cosine of B minus A. What is the cosine of B minus A? Now, one thing I suppose you can do if you have a calculator is figure out what the angle is. What is angle A and what is angle B using the calculator. Do sine inverse of 24 over 25 and sine inverse of negative 3 over 4. But I'd like to, try not to do that if possible. And besides, remember, this book is created before calculator, so we don't technically have that tool then. Okay, so here we go. Let me go ahead and start writing it out. I want to solve for, once again, what is the cosine of B minus A? Now, according to my identities that we have earlier, that is supposed to be equal to cosine of B times cosine of A, and then plus sine of B multiplied by sine of A then. Okay, so that's supposed to be the setup for it. So essentially, if I know those four components, then hey, we're pretty much good to go. Well, in terms of what we do know, we know sine of A, right, which is located over here. We also know tangent of B, which is located right here. So we're going to have to use those two to figure out what those missing components are. So once again, that's where we're going to go ahead and draw the triangles for each one. For this first one right here, we're going to draw the triangle that's in quadrant 2. So here's what it looks like then. So here's a quadrant 2. Here is going to be my angle. And we're going to now draw the triangle like so. Okay, so let's see. A is going to be angle A over here outside of the triangle. Let's see, opposite. So that means that this side over here, opposite of the angle, is 24. And then the hypotenuse is going to be equal to 25 because it's opposite over hypotenuse. With what's there, we can definitely solve for the missing side over here on the smaller part over here. And this is a perfect triangle. And that length is supposed to be equal to 7 because 25 squared minus 24 squared, and then the square root of that, that is supposed to be equal to 7, just to save you a little bit of time. But be very careful. Again, we're in quadrant 2. And quadrant 2, the horizontal component, the part that we're solving for, you can see it's x, which means that it's now in the negative direction. So what that means is this is actually equal to negative 7 over there. So that's the tricky part over there, okay? And for that one, we can then now solve for the missing part that we need, okay? But there's the triangle that's on the left then. Now, for the other one, we're going to go ahead and set up another triangle, but this time for angle B. This time, B is located in quadrant 4. So I'm going to go ahead and draw a triangle, a generic one, that looks like a quadrant 4 triangle. So it looks something like this over here, okay? Because this is going to be my angle, okay? And so that's going to be my angle B going all the way down to quadrant 4. Now, tangent is supposed to be the opposite over the adjacent. So that means that this side over here, opposite, that's going to be equal to negative 4 because our ratio is negative and y is negative in quadrant 4. Whereas the horizontal, that is going to be equal to 3 because of the 3 that's in the ratio. Okay, it wouldn't be negative 3 and then comma 4 because it wouldn't fit in quadrant 4 then. Well, now that we have both legs, then that means that we can solve for the hypotenuse. So 3 squared plus negative 4 squared is equal to 5 when you take the square root of it. So right there, now we have all the sides then. All right, going back to my original setup over here, I want to solve for what's cosine of B, cosine of A, sine of B, and sine of A. So let's go ahead and do that according to the triangle then. So cosine of B, well, cosine of B, I'm going to refer to this triangle over here, right? B, once again, is located over here. So cosine of B, that's going to be the adjacent over the hypotenuse. So then that means that cosine of B is going to be equal to 3/5 then, okay? Multiplied by the cosine of A. Well, now we're going to look back at this triangle over here and find a cosine of that angle. So cosine of the angle is adjacent over hypotenuse. So the adjacent side to angle A over here is going to be negative 7 divided by 25. Next, we look at now the sine of B. We're going to say plus. And then for the sine of B, we're going to go back to this triangle over here. So the sine of that angle is going to be the opposite, which is negative 4, divided by the hypotenuse, which is equal to 5, because we just solved for that. And finally, for the sine of A, we hop back into the first triangle over here. Sine of A is going to be the opposite, so that's 24, divided by the hypotenuse, which is equal to 25. So that's over here. And also, well, we have that over here as an answer too. Should have looked at that over there. But there you go. That's what the answer is numerically then. So put it all together. Looks like it's going to be 3 times negative 7. So that's negative 21 divided by 125. And then plus, or actually minus in this case, 24 times 4, that's equal to negative 96. And then 125 also. So if I add the two components together, that looks like it's equal to negative 117 over 125 then. So that's going to be my final answer. All right. All right. So I think that'll do it for now. Thank you so much for watching. And I guess I'll see you next time then. Okay. Goodbye.